Okay, folks. So I'm trying to screencast this so that or record a screencast so that people who are quarantining can watch it because this is much easier than having them into Zoom and setting up like a whole nother Chromebook, and that would just suck. So hopefully this will work. No, you're not getting filmed. It's just the mic. There's no camera at all. So it's just the mic and the screen. Yeah. Hell yeah. What's that? Oh, yeah. Maybe. We'll see. We'll see. Okay, so we're going to talk about intermolecular forces, but first let's talk about what does that even mean. So again, you have your notes sheet to take these notes on. I strongly suggest you use it. So just starting with the prefixes, just starting with the root words. Inter means between. So if I have an interview, it's between me and somebody else. If I have an interaction with someone, it's between me and them. Intra means within. So for example, if I were to, Carmen, go to college and play an intramural sport, I would be playing on a team of students at my college against other students at my college, not against a different college. So intra means within. So our intramolecular forces are basically the chemical bonds. They're the forces of attraction within a molecule. So it's the bonds holding the atoms together, the attraction of the electrons to the atomic nuclei, and the sharing of those electrons. So that's what an intramolecular force is, those chemical bonds. Our intermolecular forces are going to be attractive forces between molecules. So how do different molecules interact with each other? So if I were to draw a water molecule, I will do this. I usually do this on the board, but I'll do it on the screen today. So if I were to draw a water molecule, this would be my intramolecular force, which is the bond. And then if I were to draw another molecule next to it, again, I would have some intramolecular forces, but I might also have some intermolecular forces of attraction between two molecules. Okay? We're going to talk more specifically about water and how these things work in a second, but just to get you used to that before we talk about the chart at the top of the page. Okay. So intra, within, inter, between, this is what we are focusing on today, the intermolecular forces. But first I want to put them in context. So this chart, you don't need to know everything in this chart, like the stuff about ideal gases or the units or most of the stuff on top here. But I really like this chart because it does set things up between the intermolecular forces and the intramolecular forces and shows you that this is a continuum. Just like polarity was a continuum, and we sort of arbitrarily decided that at some point we were going to call it ionic, or at some point we were going to call it polar or nonpolar. The same thing is true for our forces here. So we have strong forces, which are our bonds. Our chemical bonds are hard to break. It takes a chemical reaction, it takes a fair amount of energy to separate two atoms that are bonded together with a covalent bond or an ionic bond. Our intermolecular forces are weaker. So generally speaking, they are weaker than the bonds, all of the bonds that we have been talking about. I'll give you a sort of exception to that. If you think about it, these balloons are tied together in the center, and it would take a little bit of work, probably not too much work because I didn't do it very carefully, but it would take a little bit of work to get them separated without popping them. However, if I stick the balloon to the wall, it's not going to take any work at all for that to come off the wall. right? So I didn't have to do anything really to take that off the wall. That's the kind of force of attraction that we're talking about between molecules in our intermolecular forces. Okay. So we're going to start talking about these different kinds, and notice that they all have sort of a continuum to them. We're going to start on the weak end. On the weaker end. The first force we're going to talk about is our London dispersion forces. You can just call them dispersion forces. Either term is fine. And what this is a temporary dipole, instantaneous, that's caused by the random movement of electrons in an atom or molecule. So it's tiny and it's temporary, just for a flash of time. And we can get dispersion forces in all molecules. Everybody has dispersion forces. Polar molecules, nonpolar molecules, even atoms of our noble gases that have absolutely no interest in bonding with anybody or sharing or gaining or losing electrons, they have dispersion forces too. So the picture up top is showing you a helium atom, and it's got 2 electrons. And every so often, remember that these electrons are not stationary. Well, you know, when we're drawing them, I can't draw them as moving around constantly, but that's what's happening. So at any given moment in time, both of the electrons could be on one side of the atom as they're moving around, just from the random motion. If that happens, then all of a sudden we get a little tiny dipole within that atom, where one side is a little bit negative and one side is a little bit positive. If that helium atom comes up right next to another helium atom during that moment when it's just very temporarily polarized, then it can also get its positive side can attract the electrons of this atom to be be pulled towards it and create a little bit of a dipole in the next atom. So it can be kind of like, you know, a drop of water falling into a still pond. You know, it sends ripples, but it's immediate and it's washed away, and you know, there could be a drop somewhere else at any given point in time. So the key thing here is that everybody has dispersion forces. So if you were asked to identify what forces are present in a molecule, your answer is always dispersion forces. There may be others as well, but everybody has dispersion forces. This is just another illustration of the helium atom idea, showing again that we've got 2 non-polarized helium atoms just hanging out. If one of them suddenly has 2 electrons on one side, then we create this polarity, and we can then create an attraction between the atoms. They get just a little bit sticky, not bonded together, not even close, but just a little bit sticky for just that brief moment. And that affects how they behave. If I have a big tank of helium gas, and I'm measuring things like pressure and things like that, then that's going to be affected by this tiny little bit of stickiness. And the same thing is true for molecules. So I can have an iodine molecule, which is completely nonpolar. We've got 2 iodines. They both have exactly the same electronegativity, totally equal sharing of the electrons. But just by random chance, at one point, electrons could be a higher density around one of the iodines and lower around the other, and that creates that instantaneous polarity that's going to get washed away as soon as the electrons move on, right? But it's enough that we can create a little bit of attraction between these non-polar molecules. And we're going to talk about what effect that has on the properties tomorrow. So that's our dispersion forces, very weak. But notice that even within our weak dispersion forces, on the weak side, we've got a range. Some are weaker than others. And the strength of our dispersion forces is going to depend on the size and shape of the molecules. So that's going to determine a little bit about the strength. Imagine if you have a bigger molecule with more electrons moving around, there's maybe a bigger chance that some of them are going to get stuck on one side than the other. And so larger molecules are more likely to have bigger London dispersion forces. And again, we'll talk about that more tomorrow. Okay. So we're going to move on from here. We're going to move on to the next strongest force, which is our dipole-dipole interaction. And this is where we have attractive forces between permanently polar molecules. So like an HCl molecule, we've been working with this a lot. We have higher electronegativity of the chlorine, pulling those bonding electrons to this side, making it just a little bit negative, making the hydrogen side just a little bit positive. If we have two of these hanging out together, then the chlorine of this one is going to be slightly attracted to the hydrogen of this one, because this one's a little negative, or this one's a little positive and this one's a little negative. So that, because these molecules are permanently polar, it's not a temporary instantaneous polarity, they're always polar in this direction, then the force of attraction between them is going to be stronger. And it's going to last longer, so it's going to have more of an effect on the behavior of the molecules than the dispersion forces. And again, the strength of the polarity here. So not the size and shape can affect this as well, but one of the main things that's going to determine how strong this attraction is going to be how polar is this molecule. What is the size of the dipole? If we have a more polar molecule, it's going to have a stronger negative and positive side to it, and there's going to be a stronger force of attraction. And so this also illustrates the way we usually depict these things. So a bond is going to be a straight line, or a solid line, and a dotted line is usually what we use for an IMF attraction, so an intermolecular force, indicating that it's not as strong as a bond, but there is a connection being made there. And this is what we can see in our water molecules. Where each one of them has a dipole pointing towards the oxygen end. Sorry. And so the forces of attraction between them are going to be from the positive end where the hydrogens are to the partially negative end where the oxygen is. Okay, so we're going to have attractive forces based on the polarity of the molecule. And this is drawn, and I drew the water molecules with just two simple molecules here. But that's not what's really happening. I have this water bottle, and it's, unfortunately, because I haven't been drinking enough water today, it's still mostly full. There are billions of water molecules in here. And so there are billions of these connections being made and broken all the time as I'm sloshing the water around. So our positives and negatives are going to attract each other. Our same charges are going to repel each other. And when we get a whole bunch of molecules together, they're going to try to organize themselves in a way that maximizes the attraction and minimizes the repulsion. Not quite as strongly as something like an ionic crystal lattice, where our positives are surrounded by negatives and our negatives are surrounded by positives. But they're going to try to get to that level if they can, depending on how quickly they're moving around. Okay, so the next type of interaction is called a dipole-ion interaction. And this is where we're taking this a little bit out of the realm of just covalent molecules and bringing ions into the mix. So a dipole-ion interaction is where we have polar molecules attracted to positive or negative ions. And the classic example of this is salt dissolving in water. So sodium chloride exists as a lattice structure where we have a bunch of sodium atoms and a bunch of chlorine atoms all kind of hanging out in this big structure, with the negative chlorines being negative and the sodiums being positive. And that's a pretty strong bond, and it's a pretty strong structure. But when we dump this into water, it separates. And that's how we got the salt water to conduct electricity, because these ions were no longer stuck together in exactly the same way. They were mobile. They were separated and mobile. And that happens because water is a very polar molecule. And so the negative ends of our water molecules are going to surround the positive sodium ions, and the positive ends of our water molecules are going to surround the negative chloride ions. And because even though each individual force of attraction between a water molecule and a chloride ion, for example, isn't as strong as the attraction of the two ions for each other, when we put salt in water, we've got way, way, way more water molecules than we do salt. And so we can get, all of the water molecules surrounding or solvating these ions add up to a stronger force, a strong enough force, collectively, than the force that's holding the ions together in the lattice. So that is why most salts are soluble in water, because most ionic compounds are, because the water is polar and it will have these dipole ion interactions that separate out the ions from within the compound. And the strength of this force is also going to vary by how polar this molecule is, what the charges are on the ions, the size of the ions, etc. So not all ionic compounds will dissolve in water, but many of them do. So that's our ion dipole. And again, there's a continuum there depending on polarity and size and shape. But in terms of just looking at covalent molecules, without looking at any ions specifically, the strongest intermolecular force is something that we call hydrogen bonding. Even though it's called a hydrogen bond, it is not a chemical bond. All right, this is a misnomer, but there's a reason for it, because it acts almost like a chemical bond. It's a very, very strong force of attraction. It's a subset of a dipole-dipole interaction. So it's exactly the same as dipole-dipole, but it occurs when we get an extra strong dipole-dipole attraction, when we have hydrogen bonded to fluorine, oxygen, or nitrogen. Those are the three most electronegative elements. And hydrogen is, as if you recall, is pretty low electronegativity for a nonmetal. It's 2.1. So those chemical bonds, the intramolecular forces, are going to be very, very polar. And the hydrogen is going to be not quite H+, but almost. That partial positive is going to be pretty significant when it's bonded to any of those three. And so that's going to create a very strong force of attraction. So the hydrogen bonding of water, and also the small size and its ability to simultaneously form hydrogen bonds with multiple other water molecules, is what gives water so many of its amazing properties. And again, remember that we're not talking about 2 molecules of water. We're talking about billions of them in just a water bottle, and beyond that, beyond counting, in a lake or even your bathtub, right? Not really beyond counting. We'll talk about how to count those next semester. Okay. So just to show you how strong these are and how cool that is with water. I didn't show you guys the, did I already show you guys the astronaut video? Oh, I did. Okay. But some of you weren't here. I'm just going to show it again real quick. I forgot that I showed it to you guys. Where's my, oh, right. I don't have a mouse right now. And I'll link this in, so I'm going to skip through. This is astronaut Chris Hadfield in the International Space Station, and he's doing an experiment to figure out whether what happens when you take a wet washcloth and you wring it out in outer space with no gravity. So there's so much surface tension, so much adhesion between the water molecules that it's staying completely together, like a tube of water.
Okay, so the experiment worked beautifully.
So.
And the answer to the question is the water squeezes out of the cloth, and then because of the surface tension of the water, it actually runs along the surface of the cloth and then up into my hand, almost like you have jello on your hands, or gel in your hand, and it'll just stay there. Wonderful moisturizer.
Okay, so what I kind of wish that he had done is compared that to something, something like alcohol or something like that, to really make an experiment to show the difference between water versus other substances. But you guys are going to get to do that hopefully on Friday. If not Friday, then definitely Monday, when we have a lab where you'll get to play with different polar and non-polar substances and see how they behave. So at the, let's see, where are we at on time? Oh, good. At the bottom of the back of your sheet, there is there are 4 sets of molecules. And what you're asked to do is identify all the types of intermolecular forces, Stephen, between those 2 molecules. So here for letter A, we have 2 molecules of carbon dioxide. Your job is to figure out what intermolecular forces will be in effect between these 2 molecules if they're floating around together. We've got our formaldehyde and our sodium ion, a couple formaldehyde. Anyway, between the 2 molecules, think about what forces will be present. So take a couple minutes and see what you can come up with based on the notes that you've hopefully taken. Yeah. Did they what? I am a Bills fan. I still didn't understand what he said. Something about Fortnite? I have no idea. I'm sorry. Oh, I see. Probably not, no. I never really played. I just watched my nephew play. He was good, yeah. He got his share of victory royales. He's junior, so he's y'all's age. Yeah. Where's your worksheet? Oh, you're getting notes. Okay. Okay, just to get you started, guys, just to get you started, the first set is a pair of carbon dioxide molecules. Is carbon dioxide a polar molecule or nonpolar? Ali is saying nonpolar. Why? Oh, you said it's polar. Why is it polar? Okay, so these bonds are definitely polar, yes. We have polar bonds between the carbon and the oxygen. So we've got one of the things that we need for a polar molecule. What else do we need? We need polar bonds, and we need an asymmetry. Do we have asymmetry there? No. So these are going to be nonpolar. So if we have two nonpolar molecules, what kind of force is going to be acting between them? What's that? No, they're nonpolar. The bonds are polar, but the molecules are nonpolar. So I'm asking which IMF is going to be, or which IMF or IMFs are going to be active between two nonpolar molecules. Are they going to have dipole-dipole interactions? If they're nonpolar? No. Pratt's shaking her head no, and she's correct. We can't have dipole-dipole or dipole ion or hydrogen bonding if we don't have polar molecules in the first place. So for non-polar molecules like carbon dioxide, the only force is going to be dispersion forces. Okay? So CO2 is nonpolar, and it's only going to have dispersion forces. It's not going to have any of the others. Yeah, any nonpolar molecules are only going to have dispersion forces. So that's it for letter A. What about letter B? What forces are we going to have? Yeah. Yes, this is a polar molecule. We have a dipole going through the molecule like that, pointing towards the oxygen side. So it's a polar molecule, and then we have Na plus. What's that? Sodium. Specifically, it's a sodium ion, right? So we have a polar molecule and a sodium ion. What forces are going to be present? Yes. I love that you started with dispersion because every single one of these has dispersion. All of them have dispersion forces. And yes, the other force that's going to be active between these two is the dipole ion force, or dipole ion attraction. Which side of the formaldehyde molecule is going to be attracted to the sodium ion? The hydrogen side or the oxygen side? The oxygen side, yes, because remember our oxygen is a little bit negative, so that is going to be attracted to our positive sodium ion, right? What about these two? We got two formaldehyde molecules. They're both polar. We've already said we have dispersion forces because everything has dispersion forces. What else do we have here? Do we have any other forces? Yeah. Ah, great idea. There is not actually hydrogen bonding in these molecules because the hydrogen bonding has to involve a hydrogen, and our hydrogens here are involved in nonpolar bonds. The only polar bond in this molecule is carbon and oxygen. So if we don't have our hydrogen directly bonded to a fluorine, an oxygen, or a nitrogen, then it's not hydrogen bonding. And that's really important to point out, so I'm glad you brought that up. So this is not going to give us hydrogen bonding, but what is it going to give us? Yes, this is going to give us dipole-dipole. Both polar molecules. The negative side of one will be attracted to the positive side of the other. All right, that's going to be our dipole-dipole interaction. Yeah. I'm going to post the slides now that the annotated version from now. So yeah, so I'm gonna save this annotated version and post it. We're going to come back to this tomorrow. We're going to talk about how we identify, a little more about how we identify these different forces, and more specifically about hydrogen bonding, and then what does that mean for what we see in the molecules.